यस सर, प्रोबेबिलिटी आपने बोला स्टार्ट
ये शुरू करना या कुछ किया था इसका?
नहीं सर, अभी बिल्कुल स्टार्ट से ही करना है पहले।
ओके। So our second chapter is about probability, basic concepts of probability. So when we have uncertain situation, we have to measure the situation in percentage, sometimes in fraction or in ratio. That is called probability. This ratio may be 0 or maximum it may be 1. As we have in percentage, sometimes the things are 0% or maximum they are 100%. So in ratio they are measured in between 0 and 1. So before studying probability, first we go through some definitions or basic concepts of probability. First of all, we should know about the random experiment. Random experiment. So this is an activity which produces distinct results, even if it is repeated a large number of times under the same conditions. This is called random experiment. For example, we roll our dice, a coin is tossed, a pair of coins is tossed, or a coin is tossed 3 times, a coin is tossed 4 times. Okay, other than this, sometimes we pick an element, we select an element, we draw an item, we draw an element, or in other words we draw a sample, let's say. In all these activities, we don't have any intention about the outcome. If we have certain intention that in tossing a coin there should be a head, we try to get a head. If we are selecting a person or a group of persons, we have some intention in this selection, so this will not be a random selection. This will not be a random activity. Without any intention, without any interest, personal interest, if the things are coming, the outcomes are random. These results are random. So all these distinct results of a random experiment construct a sample space. For example, all possible outcomes in rolling a dice, we have these outcomes. So this is our sample space. When a coin is tossed, all possible outcomes are a head or a tail. This is our sample space in this activity. When two coins are tossed, we have this sample space. Coins are tossed, a dice is rolled. We study these things, these activities to understand the basic concepts. Otherwise, alternatively, we select an item from a container which may be a defective or non-defective. Similarly, let we select or draw or pick up two items from a box, possibly which are defective or non-defective. So we have this sample space. Either both are good, first good, second not good, first not good, second good, or both are not good. So again, this will be the sample space. So that's why in tossing a coin, rolling a dice, drawing a card, these are only to understand the basic concepts. Okay, when a coin is tossed 3 times and each coin having two possibilities, that is turning a head or a tail, then total possible cases are 2 for first coin, 2 for second coin, 2 for third coin. So 2 power 3 is equal to 8 are the total possible cases in the sample space. Similarly, when a coin is tossed 4 times, just as we draw 3 items from a container with each one having two possibilities, either the good or defective, even then the same sample space we have. But this is easy to understand that a coin is tossed 4 times and each coin having exactly two outcomes, two possibilities with a head or a tail. So 2 power 4 equal to 16, we have total possible cases. So this is the example I was talking about, that if a box, if a collection containing 10 items, each item is either defective or non-defective. We denote defective with D and non-defective with N. And we are drawing 3 items out of the total. So the sample space will be like this. Our first item may be defective or non-defective, two possible cases. Second one also having two possible cases, defective or non-defective. Third one also having two possible cases, defective or non-defective. Because necessarily we are drawing 3 items, that's why we will multiply their respective cases. 2 multiply with 2, 2 multiply with 2. So 2 power 3 equal to 8 are the total possible cases in our sample space. Sometimes we have responses like this. for a car model, or for example for any food product, how people respond: good, very good, nice, excellent, not bad. So these are also the responses. We can also deal such situations. Again, we find the percentage of the people who responds with the letter of like, and we find the percentage out of 200 or 500 people who responds dislike, and also we can find the percentage of the people who respond undecided. So we can also deal such responses and finding their percentage in the aggregate. Okay, this was our sample space, or as you see, all the sample space are the sets. So each set having subsets. These subsets are called event. So an event is a subset of a sample space. Just like the set theory, a subset may be empty, a subset may be singleton, or a subset may be having more than one elements, or it may also be the whole sample space. All these are events. Empty set as an event is called impossible event, because nothing is in favor of this event. There is no element in favor of this event. So this is called impossible event. If we consider the whole sample space as an event, as a subset of S itself, this is called sure event or certain, because everything is considered in this subset. So the probability of the happening or non-happening of this event is 100%. A singleton as a, as a subset of the sample space is called a simple event. Now we have some properties of these events. They are called equally likely if they have the same. Two events are called equally likely if they have the same chances of happening or non-happening, of occurrence or non-occurrence. For example, if a fair coin is tossed, we may have a head or a tail. So as a singleton, these are the events, simple events, and they are equally likely because the probability of a head and the probability of a tail are the same. Mutually exclusive, simply to remember, when the two events having nothing in common, their intersection is empty, they are called mutually exclusive. So two events are mutually exclusive if their intersection is empty. But if they have one more condition, that their union is the whole sample space, then they are called exhaustive. So exhaustive events having two conditions. One, that they are mutually exclusive. Another, that their union is the whole sample space. Complementary events, if one event is the complement of the other, they are called complementary. So when we combine these events with union or intersection, they become compound events. Now consider an example of the activity when two dice are thrown. Okay, when two dice are thrown, the total possible cases are 36 because each dice having six possible outcomes. So 6 by 6, 6 multiplied by 6, we have 36 outcomes. And these outcomes are stated here in the form of order pairs. In these order pairs, first component showing the outcome of first dice and second component showing the outcome of the second dice. Now we define some subsets, or you can say we define certain events in this sample space. On the basis of certain property or certain characteristic. Let me define event A, that same number appear on both the dice, on both the die. Die is plural, die is singular, and dice is the plural word. So A be the event that same number appear. This means out of these 36 outcomes, 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6 are in favor of the event A. So the probability, that means the ratio in this total is 6 out of 36. So 1 by 6 is the probability of this event. Event B, that the sum of the dots is even. So all not all black. And this cross diagonal 1 1, 1 3, 2 2, 3 1, and this one 1 5, 2 4, 3 3, 4 2, 5 1, 6 8, 4 4, 3 5, 2 6, 4 6, 5 5, 6 4, and 6 6. These dots are giving an even sum. In this case, possible sums are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minimum, the order pair with the minimum components is 1, 1, and the order pair with maximum components is 6, 6. So minimum sum is 2, maximum sum is 12. So we can easily trace out the order pairs which are giving a sum 2, 4, 6, 8, 10 and 12. So these order pairs are in favor of B, and other than these whose sum is 3, 5, 7, 9 or 11, they are in favor of C. Actually 18 order pairs are giving a sum even and other 18 are giving a sum odd. So the probability, their probability is 18 by 36 for B and C. Now look at the sums. Look at the order pairs whose sum is divisible by 4, as the possible sums are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Out of these, 4 is divisible by 4, 8 is divisible, sum 8 is divisible by 4, and sum 12 is divisible by 4. Trace out their corresponding order pairs. Order pairs corresponding to the sum 4, they are red highlighted. Order pairs corresponding to a sum 8, these red highlighted order pairs, and the order pairs giving a sum 12, this one last at the end. So how many order pairs which are which are corresponding to 4, 8 and 12? They are 1, 2, 3, 4, 5, 6, 7, 8 and 9. They are belonging to the event D. So the probability is 9 by 36, 1 by 4. Now consider an event that the sum is divisible by 3. Again, look at these possible sums. 3 is divisible, sum 3 is divisible by 3, sum 6 is divisible by 3, sum 9 is divisible by 3, and sum 12 is divisible by 3. So the order pairs corresponding to 3, 6, 9 and 12. 3, these green highlighted, 6, these green highlighted, 9, these green highlighted, and 12, the last one. These are 12 in number. So 12 out of 36 is the probability for the event E. Sometimes we consider the order pairs whose sum is 7 and also the order pairs whose sum is 11. Easily we can find their probability. Their favorable order pairs are 6 out of 36 and order pairs giving a sum 11, they are only 2, 5, 6 and 6, 5. So 2 out of 36 is the probability for H. Now as we have defined compound events, now similarly in this case we can combine these events with union or intersection. For example, if we combine F and U, F and H, last two, these two. So as we have observed that the order pairs corresponding to F, they are 6, and two order pairs corresponding to H, combinedly they are 8, because nothing in common in F and H. Therefore, we just add. Otherwise, if they have something in common, definitely we avoid a repetition, because actually in the background a set theory is working. That's why when we take a union of two sets, we avoid repetition. We consider common elements once. For example, in the case of D and A, D, when the sum is divisible by 4 and A is the event, when same dot appears, there are three elements in common. So directly we can find their union with one condition, to avoid a repetition. So in this way we have combinedly 12 order pairs in the union of D and A. So the probability is 12 by 36. Okay. We can also find the probability of the unions using formula. This yellow highlighted formula for F union H, when F union H are mutually exclusive, when nothing is common between F and H, their intersection is empty. We simply add their respective probabilities, probability of F plus probability of H. When we have something in common, then probability of first event plus probability of second event minus the probability of the intersection. This is called addition law. To find the probability of the union, we can also calculate, because every time we will not have the whole sample space. So that's why we need to apply these rules to calculate the probability of the union and the probability of the intersection. These two formula are related to addition law, one for mutually exclusive events and other for not mutually exclusive events. Now we expand this rule to 3 events, and how this addition law works for mutually exclusive events, and how this addition law works for non-mutually exclusive events. Okay, we will discuss this additional law for mutually exclusive events when we have the situation when the events have nothing common between them. Now look at the example of addition law with three events when they have something in common. The addition law for non-mutually exclusive events. Look at the statement. A card is drawn from a deck of 52 playing cards. What is the probability that the card is either a diamond or a face card or a king? We can also discuss the same the situation of mutually exclusive events. For example, a card is drawn from an ordinary deck of 52 playing cards. What is the probability that the card is either an ace or a face card or a numbered card? So first of all, look at the deck of 52 playing cards. These are 52 cards having four categories. First one is the category of club. First row showing the category of club. Second category showing the category of hearts. This one spade, and these are the diamonds. Each category having 13 cards. So first column showing, remember, first column showing ace. Ace, not a card of one. These are the aces. With the letter A for ace. Okay, and these four, these three cards in each category: J, Q, K, J, Q, K, Jack, Queen, and King, Jack, Queen, and King. These are the face cards because each one having a human face on it, and rest of 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the numbered card. Numbered card. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cards are numbered card. 1 is ace. 3 are face cards in each category. So, in this total of 52 cards, in this total of 52 cards, solution of second. Okay. So what is the required probability in this case? The card is either an ace, the probability of A, union, or the face card, union, or the numbered card. This is required in this case. As all the three sets having nothing in common, so when we find their combined probability, the probability of their union, we just add their respective probability. Probability of A plus probability of F plus probability of N. We have four aces, so 4 by 52 is the probability of A. Face cards are 12 in number. Total face cards are 12. So 12 by 52 is the probability of F. And numbered card are 36. 36 by 52. So this will be the situation when all the three sets having no common elements. Okay, the situation is different in case of third, when the card is either a diamond or a face card or a king. Okay, look at this figure. Let me consider this figure on a separate page. So we have this situation. This is our total availability. Now highlight the events we are discussing in our problem. The category of diamond. First one, the category of diamond. So these 13 cards are related to the category of diamond. Okay. We are taking the union. What is our target here? We are trying to find the union of the three categories, union of the three sets. So this is our one set, first one. Second one, the category of face cards. Face cards. These are the face cards. This one, and also this one. These three cards are the face cards and also diamond. That's why they have both the colors, yellow color and green color also. Okay. Now the category of kings. In each category we have only one king. Is it okay? This one, this one, this one, and this one. Again, this single card having all the three colors, yellow, green, and blue. These cards are also in yellow category. Now combinedly, without considering any card more than once, avoid considering any card more than once. Now collect all these shaded cards. How many cards we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 22, 22, 22 out of 52. This is our probability. This is our required answer. Actually, in this case, we have three sets. We were having three sets. 1, 2, 3. What we need to do, we need to avoid the overlapping. So otherwise Otherwise, if we simply add their respective probabilities, probability of diamond plus probability of ace cards plus probability of the king category, this is not the answer, because this is containing all the repetitions. So now we avoid the repetition. How can we avoid? Remember, here we have in this portion two layers. Here we have two layers. Here we have two layers. And in the center we have three layers. So everywhere there should be exactly one layer. This is our target now. So let's say this is our set D. This one is our set of face cards, and this is our set K. So first of all, avoid this overlapping by subtracting one layer from here. One is remaining. We subtract probability of the intersection of D and F. Okay. Now avoid this overlapping. Subtract this intersection one time. One layer. Subtract one layer from here. Remember, when we subtracted this intersection, we are having in the center two layers. Now when we are subtracting this overlapping, now in the center we have only one layer. Our second layer was of F and K. F intersection K. Now subtract this overlapping. Subtract the intersection of D and K. D and K. With this subtraction, we have a gap in the middle, because only three layers were in the middle, and we have subtracted three intersection from this total. As we subtracted the intersection of D and K, we have a gap in the middle. fill this gap, return back this gap. This gap is the intersection of all the three. This intersection is this portion, this middle portion is the intersection of all the three. Return back this intersection. So we add the intersection of D and F and K. So this becomes the formula for our problem, for the union of the three sets. Now we calculate the probability from this formula. This is now the formula for the probability of D union F union K. Which is equal to the probability of D which is how many elements in D? 13. 13 by 52 plus 12 by 52 plus 4 by 52 minus now the intersections. The intersection of first intersection is of D and F. D and F, these three elements. So 3 by 52 intersection of F and K. F and K having these four elements in common. These four elements. So 4 by 52. Our third intersection is the intersection of D and K. D, these 13, and K, these 4. This one is common. Only one element, 1 by 52. And as we are adding the intersection of all the three, so plus how many elements in the intersection of all the three? Only one. Here, this one. This one is in the intersection of all the three. So 1 by 52. Now simplify this equation. We get 22 by 52. The answer is 22 by 52. We have solved our problem with both the methods. Once again, try to understand. This was the situation we have. this was the answer. Now look at this diagram. Here we have one element, only one element in this portion. As intersection of D and F, in the intersection of D and F, we have three elements. One is already there, so two are here. Three elements are completed in this intersection. Now, in the intersection of F and K, in F and K we have four elements. One is already there, so remaining three are here. Now, in the intersection of D and K, in the intersection of D and K, in this intersection, one element, one is already there. Now, find the elements, complete the number of elements in D. In D we have 13. 3 already there. 3 are already we have. Remaining 10 will be in this portion. Now in F we have 12. We have 12. 3, 4, 5, 6. 6 already we have in this category. So remaining 6 are here at this place. In the category of kings, we have a total of 4 cards. Only 4 are the kings in the total, and 4 are already in this portion. Now sum up all these numbers: 10, 2, 12, 1, 13, 13 and 6, 13 and 6, 19, 19 and 3, 22. Again we have 22 elements in this union, because here again we are avoiding the overlapping. No element is considered twice. Just once we have considered. Now what is the answer? What is the answer in this example? What is the answer? That the card is neither the card is exactly the diamond, or the king, or the face card. Exactly one characteristics, that the card is with exactly one characteristic out of the three. Among these three characteristics, how many cards having exactly one characteristic? Look at this diagram. These 10 cards, I need to avoid this color. Okay, only these 10 cards and these 6 having exactly one characteristic. These two cards having two characteristics, because these two cards are diamond and also the face cards. These three cards are the king and also the face card. This one card having all the three characteristics. This one card is a diamond, also a face card, also a king. But these two categories, these 10 and these 6, having exactly one characteristic. So only 16 cards are there which have exactly one category characteristic. So this is our answer for B part. Okay, also we need to go through this exercise. Finally, we have concluded that how we find the probability of an event with this ratio. Number of elements in A divided by the number of elements in S. That's mean in the numerator we have the favorable cases for A, and in the denominator we have total possible cases. So this is called a classical way to find the probability of an event. Remember, this probability of an event having two characteristics. That this probability is always from fall between 0 and 1. This probability is always in between 0 and 1. It may be 0 when the event is empty. It is 1 when the event is the whole sample space. And total probability is always equal to 1. Okay. Determine whether these events are mutually exclusive or not. So you have to consider all these and trace out which statements having two mutually exclusive events. Also, we have another example in which we need to find out some mistakes. Yes, in this example, find out the errors. Find out the errors. In first example, how we find these errors. In first example, the probability of an automobile salesperson will sell 0, 1, 2, 3 or 3 cars on any given day in February are respectively. These are the chances. The chances to sell out 0 car is 0.19. To sell out 1 car, the chances are 0.38, and chances to sell 2 cars 0.29, and probability to sell out 3 cars 0.15. What is the error? This total probability must be equal to 1, not exceeding 1. So this will be the error. This sum is exceeding 1. In B part, the probability that it will rain tomorrow is 0.4. The probability that it will not rain 0.52. Again, total probability is exceeding 1, is not equal to 1, because we have only two possible cases. Either it is raining or it is not raining. So even then, total probability must be equal to 1, which is not in this case. So this is the error. In this part, a probability of something is given in negative, which is wrong. A probability must be in between 0 and 1. It may be 0, yes, okay, but not exceeding 1. It always fall between 0 and 1. But in this case, here we have a probability in negative. So this is an error. Also in this case, the probability of selecting a heart 1 by 4, the probability of selecting a black card 1 by 2, and the probability of selecting both a heart and a black 1 by 8. So which is also wrong. We have to deal this problem in a different way. First of all, we must trace out the categories. Our one category is of a heart, so total hearts are 13. 13 out of 52. The answer is 1 by 4. Okay, that's fine. The probability of selecting a black card. Black cards, half of the cards are red and half of the cards are black here in this case. This and this 13 and 13, 26 cards are black and 26 cards are red. Okay. What is the probability of a black card? Favorable cases are 36 divided by 52. So 1 by 2, that's again fine. This is correct. And what is the probability of selecting both a heart and a black? A heart and black. That a card is heart and black. This means we need to collect here the cards having both the characteristics, that the card must be a heart as well as a black. So look at the collection. Heart, these 13 are heart, and black, and black. So there is no card which is a heart and also a black one. This probability is wrong. This probability is wrong. This is the error. Here this probability is 0 because no card is heart as well as black. So the probability is 0. So this is the error here in this case. Okay, sometimes we have a situation to find the probability of drawing two cards. In previous example, we have discussed that we draw a single card, which is either a diamond or a face card or a king. Now we are drawing two cards. Two cards are drawn out of 52 playing cards. What is required? We need to find out the probability that both are heart. One is heart. One is heart. Heart are exactly one is heart. In our selection. In our selection. All these findings are about our selection. None is heart. At least one is heart. At most one is heart. Okay, it depends how we draw these cards. Either with replacement or without replacement. Without replacement is the general case. And it has no need to mention. If it is not mentioned, as in this exercise, two cards are drawn, simply two cards are drawn. So it is understood here that it is a general case. What is the general case? That these cards are drawn, either we are picking both the cards at the same time, at once, or they are drawn without replacement. So this is a general case. No need to mention here that these cards are drawn without replacement. No, it is understood. Remember, when it is not mentioned, here I have also placed a note here. Sometimes cards are drawn with replacement. With replacement. If it is not mentioned, then it means that the cards are drawn without replacement. If the cards are drawn with replacement, this is necessary to mention here. If it is not mentioned, it is understood that the cards are drawn without replacement. What is the difference? With replacement and without replacement means we draw first card, finding the probability, or we check it and send it back to the aggregate before the next draw. In this way, let me find the probability that both are heart. So the probability of first one to be a heart is 13 by 52. And we have replaced this card. We have sent back this card to the aggregate. What is the effect? In this way, the favorable cases as well as the total possible cases remain the same for the next draw. As in next draw, we are interested again in a heart. So the probability of second card to be heart is again 13 by 52, because in this draw again the availability is the same. This is the case of with replacement. One is heart. One heart means exactly one is heart in our selection. So this one heart may be first one or second one. If it is first one, second will be from the other category. If it is second one, first one should be from the other category. Because if we divide our deck of 52 playing cards in two categories, one is heart, other is not heart. So heart category is containing 13 cards, and not heart category containing other than 13. Other than 13 are 39 cards. Remember this one. When a card is not heart, this means it is coming from other category, and other category containing 39 cards. So what happens when we need to find the probability of one heart? It may be first one or it may be second one. There are two options here. Remember, in both of these options, we are drawing two cards. Don't forget the activity. In our activity, two cards are drawn. So whatever is the situation, we are drawing two cards. In these two cards, one is heart. This may be first one or it may be second one. When it is first one, the probability is 13 by 52 for first one. For second, from the other category, 39 by 52. Because we have replaced our card before the next draw. With this situation, the total possible cases remain the same. If we don't replace, first probability of first heart is 13 by 52. Now we don't replace it. We put aside. Now the probability of second one, which is from other category favorable cases are 39 divided by 51, because our first card was heart, and after drawing we put it aside. Now the total reduced by 1. Now out of these 51, we are now finding the probability of a card which is not a heart. So the probability for second card is 39 by 51. Second option, when second one is heart, okay, second one is heart, first one is from other. Probability for first one is 39 by 52. Now we have put this card aside, not sent back to the aggregate before the next draw. Our next draw intended to be a heart. So the probability is 13 by 52 because total has been reduced by first draw. If we were drawing three cards and in the third the total will be reduced to 50 cards. A special case when we draw three cards and but with replacement. What about the probability for one heart? This may be first one, this may be second one, or it may be third one. When it is first one, here we have first one, first one. Other two are from other category. And every time we have the favorable cases and total possible cases same for all, because every time we have replaced our card to the aggregate. What happens here in this case, our second card is heart, not first and third. So first and third is from other category. Our second card is heart. In third option, our third card is heart. First and second are not. So the probability for first and second is 39 by 52 each, because we replace every time the card we draw before the next draw. Okay, just for a moment, is in the same example, if we have this situation, the case of without replacement, what happened? This probability. The probability is the same, all the options are the same, but every time the possible cases are reduced. 51, 50. First is not hard, and second is not hard, and third is also not hard. So here favorable cases are also reduced, as in this case first one is not hard, second is hard, because all hearts are available. That's why the probability of second is to be hard is 13 out of 51. This is the case of without replacement. Again, third card is from other category. As already we have drawn one from the other category. So for this, favorable cases as well as total possible cases are reduced. What happens with this option? First one is not hard. Second is not hard also. So favorable cases are reduced. Total possible cases are reduced. Now the third one is hard. 13 are available. Total 13 are available because in previous two are from the other category. So 13 are the favorable cases, but total are reduced because we have already drawn two cards and not replaced. So this is the difference. This is called probability. try to understand this thing. If you understand, no problem throughout this chapter. Throughout this chapter, we will face such a problem. Either we find the probability that all are hard, sometimes exactly one is hard, exactly two are hard, none is hard, at least one is hard, at most one is hard. Such problems we will face throughout this chapter. And also whether this selection is with replacement or without replacement. Only these two things try to understand. If you could not understand, you cannot understand probability. Also, we have two more chapters on the basis of probability. So try to understand this chapter. Try to understand these concepts. These are very necessary. In my previous result, student obtained very good grades, very good marks out of 4 sections in mechanical engineering. Near about 10 students in each section got A grade. And I think in all the 4, no one was getting D or D plus. Very good grade. But 50% students could not qualify this CLO, the CLO related to probability. 50%. 50% students could not qualify the CLO related to probability. Maybe there is a weakness from my side. Now I will try my best again. But this is a little difficult topic. I am with you. Please go through these concepts, and if you find some problem, text me anytime. Text me. I will reply, inshallah. If you have attempted some questions, you can also send it to me for checking. I will reply also, inshallah. But try to understand. Try to understand these concepts. I will send this text, inshallah, today in WhatsApp group. Okay, that's enough for today. 31 participants are there. I'm downloading their attendance. Is there any question? Okay. See you next time. Allah Hafiz.